All right, good afternoon, guys. So last time we were talking, among other things, about the closures. Oh, thanks, it's not on the thing yet. We were talking about the closures of relations. So I already defined the symmetric and transitive closure. There we go. I already defined the symmetric and transitive closure, reflexive and symmetric, and I started to define the transitive closure, but we decided that things maybe weren't so simple. So this is where we left off last time. If I see this example, we have this relation R, and we thought, okay, well, let's go through R and look at all of the things that should be there but aren't, because we want this thing to be transitive. And the idea was, by doing this and then adding the things that are missing, the relation would become transitive. And this seems reasonable because that worked for reflexive and symmetric, but it doesn't actually work for transitive, because by adding more things, you might have missing things amongst the things you added. So it's not enough just to do one round of adding. So what you would do here is you say, okay, well, I need all of those for sure. They all have to be there, or the original relation isn't transitive. So you need to take it one step further and then do that same operation to this. And then maybe the result of that is transitive, maybe it's not. If it is, great, you're done. If it's not, well, then you have to do that operation again and add all the things that are missing to this. And then maybe add all the things that are missing to that, and so on. And at some point, the hope is that you'll stop. Right? This has to stop eventually because, I mean, the worst thing that could happen would be you keep on adding things until you add everything you can add. You have the entire Cartesian product, and that is definitely transitive. So at that point, you will definitely stop. But hopefully, you will stop sooner sometimes. And in general, you do. And this goes back to the idea we had last class about composing a relation with itself repeatedly. So remember, last time we said that if we compose a relation R with itself, then we get the elements AC, where AB is in R and BC is in R for some B. So let's write that down. So recall that if we compose R with itself, then we get all elements AC, where AB is in R and BC is in R, and that's for some B. Oops. Right, that's what the definition of the composition was. And we noticed last time that this definition is a lot like the definition of transitivity. So really taking this composition makes your relation a little bit more transitive, in the sense that it adds all of these pairs that have to be there for transitivity. But by doing this, you might introduce new things that now have a missing pair. And when you take the composition, sometimes you lose things that you used to have. Right? So we need to do two things. We need to take these compositions over and over again, and we need to keep track of all of the things we're gaining while we're doing this. And eventually, this process will stop. And I'll get into exactly why it will stop and how long it will take to stop later. But for now, it's enough to understand that it has to stop sometime, because there's a limit to the amount of things I can have in my relation, right? It's the Cartesian product of that set with itself. All right, so that's the game plan. We're going to keep taking compositions until the compositions start to be the same every time. And we saw last time that does happen eventually. And the transitive closure will be the union of all of those compositions. That's what the transitive closure is. All right, so let's think about this. So this may have to be repeated. Many times. All right, and when we're done, take the union of all of those compositions And this gives us the transitive closure. So the only thing I haven't specified is how many times do you have to do this? Well, remember, when you take a composition, what you're doing is you're looking for all those pairs that have a middle element, and you're putting in the transitive version. So you're looking for all the pairs AB and BC, and you're adding in AC directly. So what that's the same as doing is it's the same as skipping over B. B is the thing in the middle. So by taking more and more compositions of this relation with itself, you're skipping more and more middle things. That's what's happening. And how many middle things can you skip? Well, you can skip as many things as there are in the set that the relation is over. So if this relation is over, say, the set A, and A has n things, then I'll be able to finish after I take at most n compositions. So how many times do I repeat? Well, this is the same as the number of, I'll call them intermediate elements. All right, and that's just exactly the size of A. So R is over the set A. Is that believable? Does that make sense to people? All right. So you might have to do at most the size of A compositions, but sometimes it will be less, and you can tell that you're done whenever you get an answer you've already got. Right? When we were computing R to the 1, R to the 2, R to the 3, R to the 4, R to the 5, as soon as you get an answer you've already seen, then you're done. Because at that point on, you'll keep getting that over and over and over again. So the transitive, if I want to say this completely clearly, the transitive closure of R over a set A is the union from I equals 1 to infinity of R to the I. But we know that's exactly the same as the union from I equals 1 to the size of A of R to the I. And the reason for that is because at some point, all of the Ri's above some number that's at most A will be the same. And when I say at most A, I mean at most the size of A. Right? So I just take the union of all of these compositions, and that's the transitive closure. And we've already seen that you kind of have to do that, right? Because if you don't do that, you end up with the situation we were in at the end of last class. If you just do it once, you might not get something that's transitive. And the transitive closure had better be transitive, right? That's the point of doing it. So let's do an example, because this seems weird until you've seen it. So let's let R be the relation 1, 1, 1, 3, 2, 2, 3, 1, and 3, 2. And this is over the set A, which is 1, 2, 3. So we know, just by looking at the size of A, we're going to have to go to at most R to the 3. And because R to the 1 is just R, that means we're going to have to do at most 2 compositions. Does that make sense? So all we have to do now is do what we did last time, right? We need to compute these compositions. So R1 is easy. That's just R. And I'll write it down here so it's easy to follow. 1, 1, 1, 3, 2, 2, 3, 1, and 3, 2. The next one I do is R squared. So what's R squared? Well, that's R follows R. So now we think, how do we compute this composition? Same as always, same as any composition, it just happens to be from one relation to that same relation. You don't need to do this, but if you find it helpful, write out the relation twice. Some people find that helpful. So I'll write it out again up here. 1, 1, 1, 3, 2, 2, 3, 1, 3, 2. If you don't find that helpful, don't do it. And now I take this composition. So I have a 1, 1 and a 1, 1, so I need a 1, 1. I have a 1, 1 and a 1, 3, so I need a 1, 3. What else am I missing? What else do I have? Anyone see? Yeah, 1, 2. Why do I have a 1, 2? Yeah, I have a 1, 3 and a 3, 2. So 1, 3, 3, 2 gives me 1, 2. I'm going to write it over here just so it's in order, because I find that's easier for me. You might not agree. Okay, and that's all you can get for 1, because I only have 1, 2, and 3. So I move on to 2. Can I get a 2, 1? Well, that would mean I would have something that starts with a 2 and something else that ends with a 1. So what starts with 2, it's just this one. What ends with a 1, it's just that one, and they don't share a middle element. So I'm not going to have a 2, 1. Do I have a 2, 2? Yep, because I have 2, 2 and 2, 2. So I keep my 2, 2. Do I have a 2, 3? Well, for that I would need 2 something, something 3. So what ends with 3? Only 1, 3 ends with 3. And do I have something that goes like 2, 1? Because that's what I would need to get 2, 3. And the answer is no, I don't have a 2, 1. So I don't have a 2, 3, so I move on to my 3's. Do I have a 3, 1? Right, I have 3, 1 and 1, 1, so I keep my 3, 1. Do I have a 3, 2? How do I get 3, 2? So 3, 2 and 2, 2 gives me 3, 2. Yep. And do I have 3, 3? 3, 1, 1, 3 gives me 3, 3. Good. So that's r squared. So I'm making some progress. So what I need to do now is compute r cubed. And this is where it's easy to get tripped up. Which one goes on top? Well, I don't remember, so let's check our notes, because that's why we take notes. We'll go back to last lecture. We'll look at this. Keep looking. R cubed is r squared follows r. So the r goes on top, the r squared goes on the bottom. Right? I needed to know something, so I looked in my notes, and now I know how to do it properly. That's an important skill. So it's r on top and then r squared on the bottom. So now we go back to our problem. I'll do this off to the side. I copy r on top, right? Because I go back here. Right here, r is on top. So, oh, I keep doing that. R is on top. And I know that r is just 1, 1, 1, 3, 2, 2, 3, 1, 3, 2. And r squared goes on the bottom. R squared is 1, 1, 1, 2, 1, 3, 2, 2, 3, 1, 3, 2, and 3, 3. As you get better and better at this, by doing more and more examples, you will have to write less and less. Right? I've copied out R like 3, 4 times now. You don't need to do that once you're good at it. But for now, rather than risking making a mistake, just do a bit of extra writing. Right? It's not that big a deal. All right, so what is r cubed going to be? So I like to go in order. So will I have 1, 1? Yes, I have 1, 1, 1, 1, therefore I have 1, 1. Do I have 1, 2? So how do I get 1, 2? 1, 1, 1, 2. Do I have 1, 3? How? 1, 1, 1, 3. All right, that's all my ones. So I start on my twos. Do I have a 2, 1? So to figure that out, if you don't see it, look at all of the things in the top one that start with 2, and all of the things in the bottom one that end in 1. So that's this, and that. And do they have a case where the second thing in the first pair matches the first thing in the second pair? Well, 2 is not 1, 2 is not 3, therefore I don't have 2, 1. That's how you figure this out. So I don't have a 2, 1. Do I have a 2, 2? Okay, how do I have a 2, 2? Yeah, that's a good way of seeing it. There is more than one way to see some of these. Do I have 2, 3? Yep. If what, sorry? No, things can go away. Yeah, things can go away. That's why we have to take these unions at the end. So in this particular case, there is a lot of overlap, but there won't always be. Okay, so do we have a 2, 3? So if we want a 2, 3, we'd look at all the things in the bottom one that end in 3. What ends in 3, that does, and that does. The only thing that starts with a 2 in the first one is 2, 2, and neither of those start with 2, so we don't have a 2, 3. That's how you figure that out. All right, so we move on to our 3s. Do I have a 3, 1? How do I have a 3, 1? Yep, so 3, 1, 1, 1 does the job. So I have 3, 1. Do I have 3, 2? How? 3, 1, and 1, 2 does it? Yeah. Do I have 3, 3? 3, 1, and 1, 3. So I also have a 3, 3. All right, so what do we notice at this point? Yeah, R3 happens to equal R2. So in this case, we could have stopped at R2, but we had no way of knowing that beforehand. So somehow we had to do this extra step. So now what we do is we take the union of these 3 sets. So R union R2 union R3 is going to be 1, 1. Do I have 1, 2? Yes. Do I have 1, 3? Yes. Do I have 2, 1? No, it's not in any of those sets. Do I have 2, 2? Yes. Do I have 2, 3? Is that in any of these sets? No. And I know that I have 3, 1, 3, 2, and 3, 3. So in this particular case, I was pretty close in R squared, but I still wasn't right. I was missing 2 elements. So I really do, sorry, that was in R. I really do need to take those extra steps. It happens in this case that R squared is equal to R3, but that won't always happen. You always need to do this many steps. Yep. In this particular case, you don't, but in general, that's what the transitive closure is. So it doesn't hurt to take that extra union. It doesn't add any new elements. But there are examples where R cubed and R squared won't be the same. And in that case, you do need to take the union of both of them. Other questions? Yeah?
How do you take transitive closure if it's like an equation that is a list of numbers?
Yeah, so that becomes a little bit trickier. We don't have a nice way of just doing that automatically. So that would require some sort of longer proof that wasn't just this method. This method works for this kind of thing. So you would either need a nice way of describing a relation. So for example, if I said something like the relation AB where A is a parent of B, what would the transitive closure be in that case? Does anyone see? a parent or a grandparent or a great-grandparent or a great-great-great-grandparent and so on. So really that would mean A is an ancestor of B. So in that case, it's not that you do this, you just try to think what would this do, because you don't have the ordered pairs explicitly. But that's how you would do that kind of operation. All right, so that's the transitive closure. Any questions about how I did this? So it's not inconceivable that you would have to do this kind of thing in about a month. All right, so it turns out that there's actually another way to look at this. And this is something that's maybe a little surprising, but also really neat. It turns out that you can represent these relations as matrices. And this is something I alluded to early on. So if you look at the matrix representation of a relation, composing two relations is exactly the same as multiplying two matrices, which is really weird. It is exactly the same, with the one caveat that if something in the final matrix is anything but a 0, you just take it to be 1, and if it's a 0, you keep it a 0. So that's not exactly multiplication, that's called a join, but it's essentially the same thing. You compute it the same way. So let's talk a little bit about that. So it turns out we can view this transitive closure another way if we look at the matrix representation. Okay, and if you don't remember what the matrix representation is, that's okay. Go look at your notes. Lecture 17, I just passed it. It's this thing right here. Right? It's exactly that. This thing on the left is the table representation. The thing on the right is the matrix representation. It has a 1 when that pair exists, and a 0 if that pair doesn't exist. Right? And the rows represent the first item, and the columns represent the second item. So that's the matrix representation. And it turns out that multiplying these things, or not really multiplying, joining them, is intimately related with the idea of composition. So given a matrix representation, I'm going to call it M sub R of the relation R, and a matrix representation M sub S of the relation S. The matrix representation of the composition of those two, so S follows R, is the matrix representation of R joined with the matrix representation of S. Okay? So this symbol here, it's a dot with a circle around it, is the join operation. And join is exactly the same as matrix multiplication, except anytime you have something other than a 0, it's a 1. So if you get a 2 somewhere in your matrix, you just change it to be 1. That's what it is. So it's the same as multiplication. But non-zero entries are replaced with 1s. So it's like a binary matrix, if you like. So is it clear what I'm stating? If you want to take the composition of two relations, you join the matrix representations of those relations. It's not at all clear why this is true, okay, but I'm telling you it is, and we'll see an example in a second. So let's go back and do the previous example in this way. Okay? So just to refresh our memories, the previous example is this thing. This is our previous example. So I would like to look at the matrix representation of that thing. So what is the matrix representation of this? What does the first row look like?
1, 0, 1.
Yeah, 1, 0, 1. Because I have 1, 1, and I have 1, 3, but I don't have 1, 2. What does the second row look like? 0, 1, 0, because I have 2, 2, but I don't have 2, 1 or 2, 3. And then what does the last row look like? 1, 1, 0. I have everything except 3, 3. So this is my matrix representation. And my claim is that I can do these compositions by doing joins with matrices. So the matrix representation of R squared, according to this, it should be the matrix representation of R joined with the matrix representation of R. So that's 1, 0, 1, 0, 1, 0, 1, 1, 0, joined with 1, 0, 1, 0, 1, 0, 1, 1, 0. Who knows how to do matrix multiplication? Okay, so if you don't know how to do matrix multiplication, this will not be illuminating for you. Doing matrix multiplication is not a requirement of this course. So if you don't know what it is, don't do this method. Right? If you don't know how to do it, it's not going to work for you. Do the other thing I described before. If you do know how to do matrix multiplication, you will hopefully find this interesting and or beneficial. All right, so to refresh your memory, the way matrix multiplication works is if I multiply two 3x3 matrices, I'll get a 3x3 matrix. That's my answer. And the way I compute it is I look at the rows of the left matrix and the columns of the right matrix. So to get the first row, first column, I look at the first row of the first matrix and the first column of the second matrix. And now I look at the corresponding entries. So that's 1 times 1 plus 0 times 0 plus 1 times 1. All right, so the very first one is 1 times 1 is 1, plus 0 times 0 is 0, plus 1 times 1 is 1, so 2. But this is a join, so if I get something that's not a 2, I just make it a 1. Or sorry, if I get something that's not a 0, I make it a 1. So that means I have a 1 up there. So if you don't believe that join is a valid operation between two matrices, I convince you hopefully that it is. What I just did was I didn't actually multiply 1 by 1. I took the and of 1 and 1, and I took the or of the next and the or of the and after that. So really, this is 1 and 1, or 0 and 0, or 1 and 1. So that's 1 or 0 or 1, which is 1. So that's how these things are connected. So that's why I get a 1 in the top left. So that's the first row in the first column. What you can do next is look at the first row and the second column. This will give me my answer for right here, right? Because you look at where they intersect. So this is 1 times 0 is 0, plus 0 times 1, which is 0, plus 1 times 1, which is 1. So that means I get a 1 up here. Does that make sense? All right, so now I do the next column. The next column is the third and final column. And for this, I get 1 times 1, and in fact I can stop there, because as soon as I get my first 1, I know I'm good, right? Because I'm adding a bunch of numbers that are positive. So I can stop right there, and you'll get a feel for that once you get better at it. All right, so now I move down to my second row. And I start with my first column. So that's 0 times 1, which is 0, plus 1 times 0, which is 0, plus 0 times 1, which is 0. So in this case, I get all zeros. So when I add 3 zeros together, I of course get a 0. So I get a 0 in that entry. And if you keep on doing this, it continues to work. So let's look at the next one. That's the second row in the second column. That's 0 times 0 plus 1 times 1, so I get a 1. And now the third column, that's 0 times 1, 0 times 1, 0 times 0, so I get a 0. So we move on to the third row. So that's 1 times 1, so I'll definitely have a 1 there. 1 times 0 plus 1 times 1, I'll have a 1 there. And the very last one, 1 times 1, so I'll have a 1 there. So this is the matrix representation of R squared. And if we look at this, what are the two things we're missing in R squared with two pairs? 2, 1, and 2, 3. And if I go back up here and look at R squared, the two pairs I'm missing are 2, 1, and 2, 3. So the matrix representation of R squared really is the matrix representation of R joined with the matrix representation of R. Of course, that's not a proof. I'm not really prepared to prove this for you because it's a lot of work for something that benefits maybe a third of you who know how to do matrix multiplication. Okay, so that takes care of R squared. And now you would continue on and do the same kind of thing. You would multiply the matrix representation of R and the matrix representation of R squared. So MR cubed is just MR joined with MR squared. And note the order there. That's one thing that's easy to get tripped up on because so if I'm computing S follows R, it's MR join MS. So the order switches. And it won't always be the same if you get the order wrong, so that's one thing you need to keep straight. It's very easy to get confused here. I'm not going to go ahead and do that. You get the same thing as you would in the other example. Any questions about this? So if you don't find this helpful, don't do it. But you should know that, that this can be done. And of course, when you've got all these matrices, you then combine them all together. So you look at an entry, and if there's a 1 in any of the entries of the matrices, then the result is a 1. So you don't get your answer by looking at MR to the n, right? You have to join or combine all of those matrices. So in fact, the operation you use, you take the OR of them. So at the end, take the union of these relations by computing the OR of the matrices. All right, so that's everything I wanted to say about the transitive closure. So my expectations for this are that, if I gave you a relation, a smallish one, because these are a lot of work, if I gave you a smallish relation, you'd be able to compute what the transitive closure is. Those who have already written the test this week know that that's not on this test, so it'll be on the final. All right, so what I'd like to talk about next is to go back for a second and talk about properties that relations can have. And this allows us to classify relations into different types. The first type of relation I'd like to talk about is the equivalence relation. So intuitively, we know what it means for two things to be equivalent. Right? We sort of know what that means. We know what it means for two numbers to be equivalent, instead of the same number. But of course, the idea of two things being equal or not is a type of relation. Right? That's what a relation is. It says when two things are related. And it turns out this idea of being an equivalence kind of relation is really useful, and it comes up a lot. And what we want is to classify what it means to be the kind of relation that captures the idea of being equivalent. All right, so let's look at some examples. So consider the equals operation. We use this all the time. It's a perfectly good relation. It's all pairs A, B such that A equals B, right? And you can define that over whatever set you like, let's say the integers. So this would be R such that we have all pairs A and B when A equals B, and this is over this set of integers. Okay? Typically, we would write 1 equals 1, but you could write 1 comma 1 in R. That'd be kind of weird, but you can do it. So why do we say that this equals relation somehow counts as an equivalence kind of relation? So why is equals expressing equivalence? And think of this in terms of the properties we already have of those relations. So if I were saying that something was equivalent to something else, would you expect that relation to be reflexive? Right, so something should always be equal to itself. Right? 5 equals 5, 6 equals 6, 7 equals 7, and so on. So the idea of being reflexive seems important, right? Because anything is equal to itself. That seems pretty reasonable. What about symmetry? So should equivalence kinds of relations be symmetric? Yeah, they should be symmetric because if A equals B, then B equals A. It doesn't matter the order you look at them in. So it seems like they should be symmetric too. So if A equals B, then B equals A. What about anti-symmetry? Should equivalence relations be anti-symmetric? So what does it mean to be anti-symmetric? Yeah?
If you have both A, B, and BA, then you have to be so you have like 1 and 1.
Yeah, so this is where it starts to get a little bit tricky, right? Because for numbers, yes, that seems to make sense. What about things that aren't numbers? So what if I wanted to compare two people, and I wanted to say that they were equal if they had the same GPA? Because that's how I view it. Would I have anti-symmetry there? Probably not, right? Because two people can have the same GPA but not be the same person. And the reason this is sort of hard to reason about, well, let's go back to the definition of anti-symmetry. And I'll show you exactly why this is hard. Oh, I guess that's lecture 17. 17? Relations, properties, anti-symmetry. So the reason anti-symmetry is kind of hard to talk about in terms of equivalence relations is because we have this equal symbol in the definition. And this equal symbol is now kind of being used two different ways. Right? Equals in this sense means the objects A and B are the same object. So if we're talking about people, that would mean that they're the same people, not equivalent people in the sense of the same GPA. So you don't need to have anti-symmetry to be an equivalence relation, because I could consider two people to be equivalent if they have the same GPA, even though they're not the same person. So anti-symmetry isn't a requirement of an equivalence style relation, even though if we're talking about numbers, it kind of happens anyway. What about transitivity? Yeah, because two things that are equal to the same thing are equal to each other. And this is something we use all the time. Anytime I prove an equality for you, I start on one side, write down this equals something, equals something, equals something, equals something, until I arrive at the other side. The thing that lets me conclude that that derivation is valid is the fact that we have this transitive property for equivalence kinds of relations. Right? The first thing is equal to the last thing because it's equal to everything in the middle. So if A equals B and B equals C, then A equals C. And that's something we rely on for equivalence relations. And if I go back to this people with GPA example, I mean, if I have the same GPA as this person and that person has the same GPA as a third person, then I know that me and the third person have the same GPA. Right? Because it feels like an equivalence kind of relation. All right, so we call a relation an equivalence relation if it satisfies these three properties. That's what it is. Yep. Right, so in this case, it's because they're the same with respect to GPA. So the only one of those four properties that has an equal sign in its definition is antisymmetry. Yeah, so that's the only place that comes out. All right. So there's lots of other examples, and we'll get to them. But first I'll just define it. So a relation is an equivalence relation if it is reflexive, symmetric, and transitive. That's the requirement for equivalence relation. So if I ask you to prove that something is an equivalence relation, what I'm really asking you to do is prove that it's reflexive, symmetric, and transitive. And we already know how to do that. Yep. That's a definition. So if it's reflexive, symmetric, and transitive, it's an equivalence relation, and vice versa. So definitions are always if and only if. Other questions? All right. So there's lots of examples. So we saw one here that's equals over the set of integers. You could also have equals over the set of sets. You could have logical equivalences. So logical equivalence is an equivalence relation as well. So there are many examples. All right. So to show something is an equivalence relation, you just show that it has all three of those properties. And the other side of that is, if you want to show something is not an equivalence relation, you show that it's missing at least one of those properties. I'll just abbreviate that to EQV rel. Show that it is missing at least one. Right? It could be missing more than one, but you need to show that it's missing at least one. Okay? So when I ask these questions, this is what I'm asking you to do. All right, so let's see some examples of determining if things are equivalence relations. So in all pairs AB such that A equals B or A equals minus B, and I'll do this over the set of integers. This is very close to something on the assignment, but that's okay. You should be rewarded for attending or watching the lectures. So if I want to know if that's an equivalence relation, I just check to see if it's reflexive, symmetric, and transitive. So first, is it reflexive? So do I have AA? Yeah, I have AA because I always have this case here, right? A equals A, therefore AA is in R, for sure, right? Because whenever A equals B, I put it in my relation. All right, so that's easy. Next I do symmetry. So I check to see if it's symmetric. The way you do all of your symmetry proofs is to assume that you have AB and then show that you have BA. So you usually do a direct proof for this. So assume that AB is in R. Well, if AB is in R, then A equals B or A equals minus B. So those are two possible cases. So we'll do a proof by cases. This is going to be case 1. This is going to be case 2. So case 1, well, if A equals B, then I know that B equals A, right? Because this is just the definition of equals for integers. So since A equals B, we know that B equals A. And therefore, BA is in R. Right? Because if B equals A, then BA is in R. So that's case 1. Case 2 is maybe slightly trickier. If A equals minus B, well, I'd like to prove that either A equals B, which we're unlikely to be able to do, or I'd like to prove what? I'd like to be able to prove B equals minus A, because then I would have BA in R. And is it true that if A equals B, if A equals minus B, then minus A equals B?
Yeah.
Yeah, I just multiply both sides by minus 1. Right, so minus A equals minus minus B, which is just B. Okay, and because A equals minus A equals B, I know that BA is in R. So there were two cases to consider, right? There is the case when A equals B and the case when A equals minus B. In either case, I arrive at the conclusion that BA is in R. So that must mean that BA is in R, because one of those two has to be true. So, I mean, it could be that the first one is false, though, right? And I need to consider both. So the first one is only true under the assumption that A equals B. So I could have 5 minus 5 here, and in that case A does not equal B, but A equals minus B. Alright, so that proves that it's reflexive because AB could be anything. So no matter what AB is, if AB is in the relation, then BA is in the relation. That's the definition of symmetry. So in either case, BA is in R. So I started with the assumption that AB was in R, and I proved that BA was in R too. So that's exactly what it means to be symmetric. Does that make sense? This is a direct proof of symmetry. All right, and then the final thing is transitivity. And sometimes this is a bit of work. So let's go through that. The way you prove transitivity is also typically using a direct proof. So assume AB is in R and BC is in R. We want to show that AC is in R. That's our goal. So in a transitive proof, you do a direct proof, and now you're assuming two things. All right, so you write down what you know. So if AB is in R, then I know that A equals B or A equals minus B, by definition. And if BC is in R, then B equals C or B equals minus C. So now I know some facts, and I need to split this up into cases. Does that make sense? Can I have cases? So what cases am I going to have? How many cases will I have, first of all? 4. So what cases will I have? Okay, so I know that these are both true, right? So I know that A equals B or A equals minus B, and I know that B equals C or B equals minus C. So if that conjunction is true, then I know that at least one of the two things I've ORed has to be true. Otherwise the conjunction would be false. So let's go through those cases. I could have A equals B, in which case the first thing would be true, so I'd be happy. But I still need the second thing to be true, and the second thing could be true if B equals C. That's one case. Another way to make it work is if A equals B, and the second thing is true because B equals minus C. That would also make everything work. Another case is if A equals minus B and B equals C. And the last case is if A equals minus B and B equals minus C. Those are the 4 cases. Why don't I have to consider the case when everything's true? Do I have to consider that case? That's not entirely true because of 0. But even if that wasn't the case, I don't need to worry about that because these 4 cases still already cover all possibilities. Right? They still exhaust everything. So I don't need any extra cases. I know that at least one thing from each of those 2 disjunctions has to be true. So those are all the cases that I have to cover. One of these 4 cases will definitely be true. And it could be, in case 1, for example, that B equals minus C as well. But I'm not going to rely on that fact, so I don't need it. All right, so let's go through this. If A equals B and B equals C, what do I know? A equals C. And therefore, AC is in R. So case 1 is easy. What about case 2? If A equals B and B equals minus C, then A equals minus C. And if A equals minus C, then AC is in the relation. Okay, so if A equals minus B and B equals C, what do I have? So, there's a couple ways to do this. You could say B equals C, therefore minus B equals minus C. Multiply both sides by minus 1. And now I have A equals minus B equals minus C, and therefore A equals minus C. And that means that AC is in R. That does the job. Yep. This one up here? Yeah, so if I have A equals B and B equals C, both A and minus C are equal to B, so they're equal to each other. A equals minus C, right? Because B is the thing that's common in the middle. Because the definition is that AB is in R if A equals B or A equals minus B. Yeah. All right, and what about the very last one? Yeah, so there's a few ways to see this. The way I like to see it is to multiply the second thing through by minus 1. So if I have b equals minus c, that must mean that minus b equals c. And now I have a equals minus b equals c, therefore a equals c, and that means that AC is in R. But there's other ways to see this. So again, we've gone through all 4 cases, and no matter what case we're in, we arrived at the conclusion that AC was in R. So this means under the assumption that A, B, and BC are both in R, we've arrived at the conclusion that AC is in R. It doesn't matter what A, B, and C are. They could be anything. So that means this relation is transitive. Okay, so now we know that the relation is reflexive, symmetric, and transitive, which means it's an equivalence relation. So we're done. Does that make sense? All right. So this is just an application of what we did previously. So let's see another example. This one's more of the same. This one's a little bit tricky until you get comfortable with notation. So it's a comma b such that m divides a minus b. And this is for some positive integer m. And this is over the integers. So m is just some variable. We're not going to use it. We're going to write it, but I'm not going to say what it is. It's just some variable. And I would like to know, is this thing an equivalence relation? That's the question. So we start with reflexive. So does m divide, so is AB in this relation? So AB is in R if and only if m divides a minus b. And we're asking ourselves not if AB is in the relation, but if AA is in the relation. So really I want to know if it divides a minus a. So does m divide 0? Does m divide evenly into 0? Yeah, it goes in 0 times. So m does indeed divide 0. And notice that it doesn't matter what m is. Right? M could be any positive integer. All right? So this is reflexive for any choice of m. It doesn't matter what choice of m we use. So we move on to the next thing, and that's symmetric. So assume that AB is in R. Therefore, m divides a minus b. And what that means is that you can write a minus b as some integer times m. Right? That's what it means to divide. Right? That's what it means for m to divide a minus b. It means if you take an integer number of m's, you get a minus b. All right, so a minus b equals km. That's great. But what I'm trying to prove something about is what? What am I trying to work towards? I want to show, and this is why you write down what you want to show, exactly that. I want to show that m divides b minus a. That's my goal, because if m divides b minus a, then ba is in R. So I know something about a minus b, but what I want to know about is b minus a. So how do I get from a minus b to b minus a? Yeah, I multiply by -1. So I take the negative of that, because if I have minus a minus b, that's exactly the same as minus a plus b, which is the same as b minus a. So this is good. I'm making some progress here. I know about a minus b. I know it's km. But what I want to know about is b minus a. But luckily, I can just take the negative. So I know that a minus b equals km. And therefore, minus a minus b equals minus km. And I know that minus a minus b is exactly the same thing as b minus a, which is nice. And if k is an integer, then minus k is also an integer. So minus k is some integer. So that means that m also divides b minus a, because I've written b minus a as some integer times m. Does that make sense? Is it okay? All right, so that means it is indeed symmetric. And now I need to prove that it's transitive. And the way that you prove that it's transitive, just like always, is by assuming you have two pairs there. So you assume the pairs AB and BC are in your relation R. And then you write out what that means. So this means that M divides A minus B, and this means that M divides B minus C. And now you write out what that means. Well, if M divides A minus B, that's exactly the same thing as saying A minus B equals K1M for some K1 that's an integer. And this means that B minus C equals K2M for some integer K2. All right. And notice that these are different, right? K1 and K2 might be different. They almost certainly will be. That's strange. Is that my mic or something going on? Okay, so it stopped when I hit mute, and that's kind of weird. All right, in any event, so it's important to remember that K1 and K2 could be different. This is a very common mistake, is to write K twice. That doesn't work. All right, so now that I have this, I start subbing these in and see if I can get anywhere. So I know that A minus B equals K1M and B minus C equals K2M. It's hard to do any kind of direct substitution. So when you get stuck, what I suggest doing is adding the equations together. Right? If it's not obvious where to substitute, just add the equations together and hope for the best. So I know that A minus B equals K1M, and I know that B minus C equals K2M. So if I add those together, I get A minus B plus B minus C equals K1M plus K2M. And now notice that that minus B and plus B cancel. So I get A minus C on one side, and I have a common factor of M on the other side. So I can say K1 plus K2 all times M. Yeah? No, the M is definitely the same. So the M is some variable that I'm not telling you the value of. It's definitely the same for the entire relation. All right, so this means that A minus C equals K1 plus K2 times M. K1 and K2 are both integers, which means their sum is also an integer. So A minus C is some integer times M, which by definition means that M divides A minus C. So M divides A minus C. All right, so that means that AC is in my relation. So what have I done? Well, I've assumed that AB and BC are both in the relation, and now I've proved that AC is in the relation. So that's exactly what it means to be transitive. Does that make sense? All right. So let's see some more examples. Here's another one. I want to know, is the divides relation on the integers an equivalence relation? Right, so remember that's the pairs A, B such that A divides B. All right, so first we check, is it reflexive? So is this relation reflexive? That's the same as asking, does a number divide itself? Yeah, it does, right? A divides A, because the answer is 1. Is that actually true? Yeah, so there's this catch 0, but I can save the day by saying I didn't specify what this was over. Well, I did say it was the integers, so I'm going to say it's the positive integers. And now everything is okay because 0 is not included in there. So that's kind of nice. A divides A as long as A is not 0. That's good. All right, so we know that it's reflexive. For reasons that will become clear in a second, I'm going to skip symmetric and I'm going to go to transitive. So I want to know, is this relation transitive? So if A divides B, then I know that B equals K1A. And if B divides C, then C equals K2A. And K1 and K2 are integers. All right, so at this point, what I'm trying to show is that A divides C. So C is an integer times A would do that. So C is K2A, which is kind of nice. Sorry, yeah, K2B. Good catch. Yeah, K2A we're already done. So C is K2B, and I know what B is, it's K1A. So C is K2 times K1 times A. Well, if K1 and K2 are positive integers, then K1 times K2 is also a positive integer. And therefore A divides C. So no matter what A, B, and C are, if A divides B and B divides C, then I know that A divides C. So this relation is transitive. But now let's go back and look at symmetry. So is this relation symmetric? No, why not? Right, 1 divides 2. But 2 doesn't divide 1. And this is exactly how you show a relation isn't symmetric. You give me the pair such that the symmetric version of that pair, the flipped version of that pair, isn't present. That's how you disprove symmetry. All right, so that's an example of something that's not an equivalence relation. Because it is not symmetric. So if we had been lucky and checked for symmetry first, I wouldn't have had to do the other two things. Right? That's handy. All right, let's see another example. This one's also kind of tricky. So the example is this. Let's say R is the set of pairs A, B such that the absolute value of A minus B is less than 1. And this is over the set of real numbers. All right, so let's do the usual checks. Is this reflexive? Well, the absolute value of A minus A is definitely 0, and that's always less than 1. So this thing is indeed reflexive. What about symmetric? Well, for symmetric, you assume that AB, I'll call this relation, oh, I did already. I'll assume AB is in R. What does that mean? It means that A minus B is less than 1. And I want to know something about the absolute value of A minus B is less than 1. I want to know something about the absolute value of B minus A. What's the absolute value of B minus A? It's exactly the same thing as the absolute value of A minus B. Right? Because A minus B, as we just saw, is minus B minus A. And absolute value lets you ignore the minus. Right? You always get something that's positive. So the absolute value of A minus B, sorry, of B minus A, is exactly the same thing as the absolute value of A minus B. So, if the absolute value of A minus B is less than 1, then the absolute value of B minus A is also less than 1. And therefore, BA is also in the relation, so this relation is symmetric, which is kind of nice. What about transitive? Does it seem like this thing is going to be transitive? It seems like that's unlikely, right? Because these numbers A and B, they can be pretty big, and it seems unlikely that, when I subtract and take the absolute value, that it'll always be smaller than 1. That doesn't really seem correct. So our intuition says this is wrong, so what you might want to start doing is look for counterexamples. Right? So look for A, B, and C such that A and B, such that AB is in the relation, and BC is in the relation, but AC is not in the relation. So any ideas? So 1, 2, and 2, 3. So let's try that. So what you have to do is first make sure that each one of those really is in the relation. So is 1, 2 in the relation? Well, the absolute value of 1 minus 2 is 1, and that's not less than 1. So that means 1, 2 is not in the relation. So right off the top, this won't work as a counterexample. You need to make sure that the first pairs you talk about really are in the relation. Yeah? 1, 1.5, 1.5, and 2. All right, this is good. So let's work with that. I know that, let me put it like this. I know that the absolute value of 1 minus 1.5 is the absolute value of minus 0.5, which is just, which is 0.5, which is less than 1. So the first thing is definitely in the relation, so we're off to a good start. Now we check the second thing. So the absolute value of 1.5 minus 2 is the absolute value of minus 0.5, which is 0.5, which is less than 1. So that's good. So that means these really are in the relation. But now we need to look at 1, 2. Because if this thing were transitive, I would have 1, 2 in this relation. But the absolute value of 1 minus 2 is the absolute value of negative 1, which is 1, and that is not less than 1. So if this were transitive, this pair, 1, 2, would have to be in the relation. But I just showed that it's not in the relation. Okay, and therefore, this relation is not transitive. So this is an important thing to remember when you're coming up with counterexamples. Right? It's not enough just to write down your counterexample and leave it at that. Right? There's more to it than that. You need to show that your counterexample really is a counterexample. And that's what we did here. We have to show that these two things are in the relation, but the third thing that should be there is not. So I want to give a small preview of what's to come next time. And that is a consequence of equivalence relations, and it's called an equivalence class. So equivalence relations naturally partition your set. So let's say you have a relation R over a set A. If R is an equivalence relation, it naturally partitions A into a bunch of parts, and everything inside that part is equal to everything else inside that part. Okay, so let's go back and talk about this GPA example. Okay? Or let's make it even simpler and talk about just grades in a single class, so you don't even have to compute anything. So I'll consider two people to be equivalent if they got the same grade in Comp 1805. And this relation, I'll make it over the set of all students in this class. So if you look at every person in the class, they got a particular grade. And they're equal in some sense to everyone else who got that grade. So in this class, you'd have this set of all students, and within that, you'd have the set of all students with an A+, the set of all students with an A, an A-, an A+, an B+, and so on. And if you look at all of those sets, every single person in this class is in exactly one of them, for sure, because everyone ends up with some grade. And if I take the intersection of all of those sets, it's empty, because no one has more than one grade. So everyone has at least one grade, and no one has two grades. So that means we have what's called a partition. A partition of a set is you break it down into a bunch of subsets, such that all of the subsets are disjoint, they have nothing in common, but when you take the union of all of the subsets, you get the original set back. And this is what an equivalence class, an equivalence relation does, is it produces these equivalence classes. So the classes would be the set of people who got an A, the set of people who got a B, the set of people who got a C. So that's something that we use equivalence relations for, and it's something that's really important. All right, so I'll end here, and we'll pick back up with equivalence classes next class.